In chemistry, group theory can explain the spectroscopic transitions in a molecule qualitatively. Each molecule possesses quantized energy states, known as molecular energy levels. These include electronic, vibrational, and rotational energy levels arranged hierarchically. Electronic states have multiple vibrational levels, and each vibrational level further has multiple rotational levels. Each transition is associated with a ground state and several excited states. When a molecule absorbs energy that matches the energy gap between two states, a transition occurs from a lower state to a higher state. However, not all transitions are allowed. The probability of a transition is governed by selection rules, which arise from molecular symmetry and interaction of the molecule with electromagnetic radiation. Chemical group theory provides the mathematical framework to analyze molecular symmetry and to determine which transitions are allowed or forbidden. Let's imagine a molecule which has n number of molecular orbitals. Here, we have the highest occupied molecular orbital, which is HOMO, and the lowest unoccupied molecular orbital, that is LUMO. As we know, each orbital behaves like a wave function and is represented by psi. Each wave function can be represented by an irreducible symmetry operation within the molecular symmetry. We can say psi HOMO is tau I and psi LUMO is tau F. Tau I is the irreducible representation of HOMO and tau F is the irreducible representation of LUMO. This can be evaluated using a character table of the corresponding molecular symmetry. Now, our job is to find out whether the electronic transition from HOMO to LUMO is allowed or forbidden. We can do it using the concepts of quantum mechanics and/or the concepts of group theory. We know electronic transitions are associated with dipole moment change. Because light is an electromagnetic wave, its electric field oscillates in a direction defined by x, y, and z. The dipole operator of the molecule decides how the molecule interacts with that electric field. Dipole moment of a molecule arises due to the polarity difference between the atoms. A dipole moment is a vector operator. It is a product of the magnitude of charge and the distance between the two atoms. So, in a molecule, we will expect multiple dipole moment vectors. If we add all the dipole moment, we can find out the net dipole moment of the molecule, which can be resolved in x, y, and z directions. So, the dipole moment of a molecule is expressed in terms of x, y, and z. Therefore, it has its own irreducible representation under a molecular symmetry. For example, in C2V point group, dipole moment transforms like A1, B1, and B2. Because the x, y, and z axis transform accordingly. Therefore, the dipole operator in C2V molecule transforms as A1 plus B1 plus B2. Now, we will have to compute the transition dipole moment integral for a transition. The transition dipole moment integral involves the molecular dipole moment operator and molecular wave functions. It quantifies how effectively a molecule can interact with the electric field of incident light. The light supplies the oscillating electric field, while the molecule provides the dipole moment responsible for the transition. It describes how strongly the electric dipole interaction couples an initial and a final quantum state. If the coupling is zero, the transition is forbidden. If it is non-zero, the transition is allowed, and its magnitude determines the intensity. This can be evaluated by using the concepts of quantum mechanics and group theory. As per quantum mechanics, transition moment integral can be calculated by integrating the product of psi I, dipole moment operator, and psi f. Imagine a molecule. You have a HOMO and a LUMO and a dipole moment operator. The HOMO and the LUMO are wave functions, and they have their presence across the molecular space. So, if I want to calculate, then I will have to integrate it in the whole molecular space. Imagine space divided into tiny points. Now, think of the molecule surrounded by millions of tiny boxes in space. Each box gives a small contribution to the wave function. At each tiny point, we evaluate the integrand for transition dipole moment, which is a product of psi f, dipole moment operator, and psi I. So, every small region gives a small contribution to the transition dipole moment. Here, some regions give positive contribution, some give negative contribution, and some points have zero contribution. The integral simply adds all of them. So to calculate the net dipole moment, we will have to integrate it over the space. If m is not equal to 0, transition is allowed. If m is equal to 0, transition is forbidden. And the value of m determines the strength of the transition. Let's understand this clearly. Imagine multiplying three spatial functions at each point: psi f, dipole moment operator, and psi I. At every point in space, we calculate the contribution of transition moment integral, which is equal to the product of final orbital, dipole operator, and initial orbital. That number becomes the integrand at that point. Now, imagine the space is divided into four regions, such as A, B, C, and D. And we found the value of the integrated at each point like region A plus 2, region B minus 2, region C plus 1, region D minus 1. When we integrate, we sum everything, which is equal to 0. So here the transition becomes forbidden. But if symmetry aligns properly, the dipole moment of the molecule perfectly couples with the two states. Then contributions reinforce, and we might get something like region A, it is plus 2. Region B, plus 1. Region C, plus 3. Region D, plus 2. Now, the summation is not equal to 0. So, this transition is allowed. This is the quantum mechanical way to predict the transition probability. In the next videos, we will see how we can use group theory to predict the transition.